All right, welcome to the explainer. You've seen it everywhere, right? Tools like ChatGPT have just completely blown up, changing how we interact with computers. And the engine behind all this? It's the large language model, or LLM. So today, we're going to pull back the curtain and really figure out what they are, how they actually work, and, what it all means for us. Let's dive in.
For the longest time, a computer was basically just a super obedient calculator. It only followed orders. You wrote a program, gave it explicit instructions, and it did exactly what you told it to. No more, no less. But what if that whole model was flipped on its head? What if, like this slide asks, a computer could actually learn instead of just following instructions? That one shift, that single question, it changes everything. It's the foundation of this entire field.
Okay, so first things first, let's get a clear definition. What exactly is a large language model?
So at its core, an LLM is a very specific type of AI. Think of it as a neural network that's been fed a truly mind-boggling amount of text. We're talking huge chunks of the internet, millions of books, pretty much anything written down. But here's the part you really need to get. Its goal isn't to think or understand the way a person does. No, its only job, its entire purpose, is to get ridiculously good at spotting patterns in language and then predicting what comes next. And this slide really shows you that fundamental split. On one side, you've got traditional programming. It's totally rigid. It's all about if this happens, then do that. But machine learning, it's a whole different ballgame. You don't give it rules. You feed it a mountain of examples and let it figure out the patterns for itself. It's the difference between telling it what to do and teaching it how to learn.
This analogy is perfect. Just imagine for a second trying to write code that could recognize every single person's unique, messy, handwritten letter A. The slants, the loops, you'd go crazy. You literally couldn't do it. So with machine learning, you don't even try. You just show the computer thousands and thousands of examples of A's. It looks at all of them, finds what they all have in common, and basically learns the essence of what makes an A an A. LLMs do that exact same thing, but for the entire universe of language.
All right, so we know they learn from data, but how? I mean, what's really going on under the hood when you type a question into that little chat box and a whole paragraph comes back? Let's break it down.
The whole thing can really be broken down into a few key stages. First, it has to break your words into something called tokens. Then, it turns those tokens into numbers in a process called embeddings. And finally, that's where the real magic happens, in this transformation step, which uses some seriously complex architecture to build a response. For now, let's just focus on those first two crucial building blocks.
Okay, first up, tokenization. See, the model can't just read whole words or sentences like you and I do. It needs to chop them up into smaller pieces, and these pieces are called tokens. A good rule of thumb is that a token is, on average, about 3/4 of a word. So short words might be a single token, but longer, more complex words get broken up.
And this is actually really clever. Take the word tallest. The model might break that into two tokens, tall and est. By doing this, it's not just memorizing a word, it's learning about relationships. It's figuring out that est is a thing you can add to words like tall to change their meaning. It's learning the grammatical building blocks of our language.
So after tokenization, we get to embeddings. This is where things get really cool. Computers don't speak English, they speak math. So every single token gets converted into a long list of numbers, what's called a vector. The best way to picture this is to imagine these numbers as coordinates that place each and every token on a giant, mind-bendingly complex, multi-dimensional map of language.
And the real power of this map is all about proximity. Words that have similar meanings, or words that just tend to show up in the same kinds of sentences, they get placed close to each other on this map. So the model learns that king is close to queen, or that book and worm often go together. This incredible web of connections is how the model starts to grasp context, nuance, and the relationships between ideas. It's not thinking, it's just recognizing proximity on a massive scale.
It really feels like this technology just exploded out of nowhere, right? But the truth is, it's been built on decades and decades of research. The history is actually surprisingly long, with a few key moments that just changed everything.
The journey starts way, way back in 1966 with a chatbot called Eliza, which was really just a simple program using clever keyword tricks. For decades after that, progress was, well, it was pretty slow. And then,
2017 happened. A paper from Google called Attention is All You Need introduced the transformer architecture. That was the moment. That was the technical breakthrough that unlocked everything we see today. From there, it just became a race of pure scale, leading to the public explosion of GPT-3 in 2020, and then the massive, massive leap to GPT-4.
So what does a massive leap even look like? Well, GPT-4 reportedly has around 1.76 trillion parameters. A trillion! And remember, you can think of a parameter as just a single connection, a single dial or knob on that giant language map we talked about. The sheer number of those connections is, well, it's almost impossible to really wrap your head around. But it's that immense scale that gives it its incredible power. Okay, so we've got these incredibly powerful, unbelievably complex models. But what are they actually good for? And more importantly, where do they fall flat on their face?
Well, at their best, LLMs are like a superpower for almost any task that involves words. I mean, they can summarize a super dense report in seconds, they can act as a creative brainstorming partner, answer incredibly complex questions, write and debug computer code, they can even translate languages with scary good accuracy. These things are literally changing entire industries as we speak.
But, and this is a huge but, they are far from perfect. For all their amazing abilities, they have some really deep, fundamental flaws we have to talk about. One of the biggest problems is something called hallucination, which is really just a fancy way of saying the model makes stuff up. Look at this example. It's asked a simple counting question, the right answer is 15. The model, though, comes back and confidently says the string has 16 letters. The key word there is confidently. It isn't just wrong, it's wrong with its chest puffed out. And that's because it's only predicting the next most likely word. It's not checking facts or reasoning. It has no concept of what's true or false, and that can be seriously misleading.
And that brings us to an even bigger issue, bias. You know that old computer science saying, garbage in, garbage out? Well, it has never been more true than it is right here. These models learn from text written by us, by humans. And guess what? Human data is messy. It's full of all our biases, our stereotypes, our flawed logic, and our mistakes. And all of that junk gets baked right into the AI's core logic. So, keeping all of that in mind, the incredible strengths and the very real weaknesses, where is this all going? What are the brightest minds in this field working on right now?
Okay, research is really pushing hard on a few key fronts. They're working on improving reasoning, trying to get these models to actually solve problems step by step instead of just guessing. They're adding multimodality, which means the AI will be able to understand not just text, but images, your voice, even video. They're building more efficient models like a mixture of experts to bring down the insane costs. And they're expanding the context memory. Just imagine being able to feed it an entire novel and then have a detailed conversation about it. And all of this progress, all of this power, it leads us to the single most important question in the entire field. As these systems get more and more powerful, maybe even more powerful than us in some ways, how do we make sure they're on our team? How do we ensure they share our goals? This alignment problem isn't just a tech puzzle. It's probably the defining challenge of our time. And it's something we all really need to start thinking about. Thanks for joining me on this Explainer.